speakers, and the first is Joe Quinnett. We'll talk about optimal crossover designs in a model with interactions between treatments and subjects.
So, welcome to the John Stifkin session. This joint work with John and me, and then afterwards you'll get the original. So I'm talking about crossover designs, and even so, this is called medical research here. I'm talking about beer. So in the crossover designs, the units, the subjects get one treatment after the other, and in my case, and the experiment that I usually do with crossover is sensory experiments, when they taste one beer after the other and they give the mark to each one. And so it's quite clear that you will have an effect of the assessor. Some do like beer and they give good marks all the time, and you will have maybe an effect of the period. You know that the first beer tastes the best, and you should have an effect of the treatment that we are interested in, and maybe carryover effects. That's to make it mathematically nice, to have a mathematical problem to solve. Whereas in reality, we try to have washout periods in between so that they wouldn't have carryover effects. But for playing around with mathematics, it's much nicer with carryover effects. And so that's the model. The measurement is direct effect, carryover effect, effect of the assessor, effect of the period, and an error. And we assume that the errors are IID. And this model is often criticized. If you neglect carryover effects for the moment, then you'll see that if you have in this model two subjects and 100 periods, you get exactly the same information matrix as if you have 100 subjects and two periods, two observations per subject. And that's clearly not realistic. For instance, if you look at the preference studies, then one consumer comparing products A and B 50 times certainly provides less information than 50 consumers comparing products A and B just once. And this is because a consumer preferring A will most likely prefer it all the time. And if among 50 you have 47 preferring product A, then you know something. But if you have two consumers preferring product A, you know nothing. So in consumer studies, therefore, an interaction between product and consumer is modeled. And we consider this extended model where the treatment effect now becomes the effect of the treatment plus an interaction between the treatment that's given to the assessor and the assessor. And we randomize this as, we model this as random, because we think that our consumer is a random person taken from some population. And there's a fixed, that's random. And for simplicity, we assume that the expectation is 0 and the variance is a constant. So that means that if an assessor gets the same product more than once, the two or more observations of the same product by the same assessor are correlated. And the correlation is written here. That's the variance of the error, and that's the variance of the interaction. And this gamma is between 0 and 1. Therefore, if a subject I gets the sequence 1, 2, 3, 3, gets the last beer twice, then these two measurements of the last beer will be correlated. And however, if the subject gets the sequence 1, 2, 3, 4, gets no repetition, then there will be no correlation. Although this model is often used in practice, at least in sensory experiments. I didn't find anybody to write to determine optimal designs for it, and maybe the reason is because it's not easy. Here's an attempt to fill this gap. So, as I said, we consider this model, and the random components, the errors, and the random interactions, they are all assumed independent. Just one remark, we assume that the effect of the unit is of the, it should be subject. We change it, and I changed it even in the title, but I forgot to change it on the slide. The effect of the subject is a fixed effect. That's because we assume that it's in reality a random effect, but with a large variance. There's a large difference between assessors. And now we rewrite it. We put the interaction to the end, so it gets together with the error, and then we see that the fixed part is the same as in the traditional model. And this will mean that we can use the methods from the traditional model with some slight modifications. The model in vector notation gets treatment design matrix, the matrix for the carryover effects of the subjects, and the matrix for the period effects. And we have a covariance structure, and the covariance is all the measurements on one subject are possibly correlated, but the measurements on different subjects will have to be non-correlated. So there's zeros all over outside these blocks. And if one subject gets only a sequence where no product is being repeated, then the covariance matrix for this subject is also an identity matrix. One thing we should remark here is that in each row there's exactly one. In each row of the treatment design matrix there's only exactly one, because you get just one treatment. You taste one beer at a time. And for instance, in the matrix for subjects, there's only one in each row because you get one subject. And this means here that if you multiply this matrix with a vector of ones, you get a vector of ones. And if you multiply this with one, you get a vector of ones. And this means we have no full rank. We don't have full rank. And the vector tau, the vector of treatment effects, is not estimable. That's clear with block effects. It's always the same. And what we do instead, we use Kiefer's result, Kiefer's 75. So if we have a linear model where a partition linear model, and we want to estimate alpha, and we can't because the A times 1 is in the image of this design matrix B, then we, instead of estimating alpha, we estimate the mean corrected alpha. And the alpha hat is the estimate for this thing. And the information matrix then is the inverse, the Moore-Penrose generalized inverse of the covariance of this, oh, another misprint, of this alpha hat. And you should note that this matrix has row and column sums 0. And Kiefer's famous result was that if you have a design such that the information matrix is completely symmetric, has one number on the diagonal and another number outside the diagonal, and maximizes the trace over a set of designs, then this is universally optimal. And so what we do here is we search for a design that has the information matrix completely symmetric and maximizes the trace. So we simplified our problem a lot by simply looking at the maximum trace of the information matrix. Yeah, we have another problem. We have the covariance. So we use weighted least squares estimate. We use a matrix which inverts the covariance matrix. And we transform our model. We transform the observations and each of the design matrices by multiplying with this matrix Q. And then we get a transformed model, and this transformed model is quite nice because it has IID errors. It should be kept in mind that we can only do that if we know the parameter gamma. So we know the relation between the two variances. Except in one simple case, if we have a binary design where no assessor gets any beer twice. Then this sigma here is a identity matrix, and we don't have to. And then also our QD is an identity matrix. We have no problems. So in this case, the information matrix is this thing here, and you see this omega orthogonal looks harmless, but it's hard to handle because we have to calculate the inverse of this matrix here multiplied with it itself, and it's a partitioned matrix, and it depends on the design. So it's not easy to handle in the model without interaction, and it's even less easy to handle in the model that we look here in with interaction in this case here. And I remember my first paper that I ever wrote was on this model without interaction, and this was in '84. And we were, all of us working in this field were pretty much stuck till in '97 a guy called Kushner, whom I was hoping would come here but didn't, published a paper which made a huge progress. And one of my colleagues says, nobody is allowed to write a PhD thesis with me who's not using Kushner's method. It's not really clear, true, but almost. So we got stuck here. Maximizing the trace of this is not easy unless you use Kushner's method. And the idea was to use approximate designs. And approximate designs in that way that the design points are the possible sequences we might give to the subjects. So it's not the single observations, it's the sequences that we have, and the weights are the proportion of subjects receiving these sequences. Remember that we try to find a design maximizing the trace of the information matrix. And if we have approximate designs, then the trace of this information matrix simplifies a lot, because we can assume by that all matrices that appear are completely symmetric. So it simplifies into this here. It actually is a number. It's a CD11 which we can calculate. It's a CD12 that we can calculate, and we have to divide by a CD22 which we can calculate. It's a trace of a matrix that we can handle. But it's that's still not the basic idea of Kushner's method. The basic idea of Kushner's method is to look at what's going on now. So the idea is that each of the CDIJ can be written as the sum of CDIJs that belong to the single sequences. So it's a convex combination of the sequences that we might give to the assessors. So that's nice and linear, and we can deal with it. Unfortunately, we have this inverse here, so it's no longer linear. So how do we get this nonlinear problem into a linear problem? We get it into a linear problem by observing that this thing here is the minimum of this of this polynomial. Simply, could have given the proof that it's the minimum, but you simply believe me, I think. The referee for this paper asked us what's the meaning of the variable x. Nothing. So it's just that's one of the fields that why mathematics is so nice. You make an easy problem maximizing a trace complicated by minimizing the maximum of a function, and with a completely meaningless variable x, and suddenly things can be done. Now, the nice thing is that this function is actually a convex combination of the functions that would belong to the single sequences. So it's linear in the sequences. And since it's a convex combination, if you have two sequences, and then any combination between the two must be between the two sequences that you had originally. So the black is sequence A and sequence B, and the red is any combination between the two. And the interesting point is that it must always be smaller than the maximum of the two original sequences. And then you try to choose the proportion of these two sequences in such a way that the minimum of the combination is at the minimum of the maximum. And the nice thing is there aren't too many sequences possible. So if, for instance, if we look at our problem, I'm afraid it's a bit too small to see anything. If we look at the case that we have 4 periods, then there are only 15 possible sequences that we can give to the abscissors. So the first one gets 1, 2, 3, 4, gets 4 different beers. Second one gets second possible sequences gets the last period repeated, and this is a particular sensible sequence. You get the same beer 4 times. These are all possibles that you can have, and now you simply have to look to calculate for each these CDIJ, calculate the sequence, the polynomial for each sequence, and then look at the minimum of the maximum sequence. And then you're done. So it can be done numerically from here. As an example, we consider the case that we have 4 periods and the number of treatments is also 4. Then we have we just look at 3 of the sequences. The blue is the one that gets each beer once. The red one repeats the last sequence, and the green one is one I added for fun. It gets beer 1 twice and beer 2 twice. And I look at the special instance that gamma is 0, so there is no interaction. That's a traditional model. And what you see here, if you give only sequence 1 to the assessors, then the minimum is at this point here. Whereas if you have a few assessors getting the red curve, then their intersection point is slightly bigger. Not very much visible, but slightly. And so this graph explains the well-known fact that the optimal design in the traditional model uses sequences 1 and 2. And the proportion of sequences from class 2, the red ones, is small. Here's the graph. I thought this was already here. I was wondering why I couldn't see it. So that's the combination. A large proportion from the blue one and a small proportion from the red one gives this whatever you violet one. And this has a slightly bigger minimum than the other ones. Here, I zoom into the graph to see it better. So that's the blue one minimum over here. The red one coming up very steep now, and the violet one has its minimum actually here. If there are interactions between assessors and products, then the situation changes. You see that the blue line is exactly the same as it used to be before. You can't see that, but I tell you. Whereas the red line now it starts lower than it used to start before. It used to start at around between 2.4 and 2.6, and now it starts at 2.2. And this means it comes up to the blue line later, and the minimum of the maxima is really here, is the minimum of the blue line. So we don't need the red one anymore. That's the proportion of sequence 1, 2, 3, 3 in the optimal design if we let gamma the correlation increase, the variance of the interaction. And you see it starts somewhere from the traditional model and it disappears pretty rapidly. And that made me quite happy, and that's actually it has to be non-zero, of course, for continuity, but it should disappear. And that's what I expected to happen, and that's why I gave this to Andrea for her thesis, hoping that she prove this, find a nice general proof that this will happen with all the time. So that's exactly what I expected when I asked Andrea to work on this model for her thesis, and I was rather surprised when she gave me the whole picture. So this sequence disappears and reappears up here, and then gets smaller and smaller, but never fully disappears. She, in her thesis, looked at the situation 3, 4, and 5 periods, and 6 also, and it turns out that in all cases we have this weird experience that the identical pairs do reappear. For 6 periods we even have that we suddenly have something that doesn't appear in the traditional model. We have sequences like this one where you repeat 2 pairs. The question that we had after her thesis was, is there a general structure? We couldn't, with her thesis, we couldn't find more than the numerical solutions for the cases 3, 4, and 5, and 6. The reason is that the formulas are simply nasty, even if you look at the even if you use Kushner's method. And so that's where we started when we got together in 2011. John and I walked alongside the sea and discussed whether we might find something general on this. And I'm now going to tell you what we did in the meantime. So the first result we had is that any design must have the trace of the information matrix less than p minus 1. So that's an upper bound that we can prove for any design if you have p periods. And if you have a neighbor balance BIBD, the best design you can get, if you have no beer repeated, then it will have the blue line here. Remember that it doesn't depend on gamma, the trace of the information matrix for this design, because there is no correlation between the observations. And there's some lag, but you see that's 3, that's 2.7, so it's not as low as this picture seems to. it has quite a good efficiency. But we thought maybe we can improve this. That's for periods here. The interesting point is if we look at the performance of the optimum design. So we knew from Andreas' work that the binary design is optimum in this interval. And it's not optimum here. And it's also not optimum here. So here we have to zoom into the graph to see any difference. So the efficiency here is really high of the binary design. So there's not, in the traditional model, the one that repeats the treatment is not much higher, but in the other one, on the other end, we win a lot. And if you look at it very closely, it actually goes up to this. So there goes our attempt to improve this bound. We can't improve it. How can this be explained that we can't really improve it? So the reason is certainly a defect of the model. So if we look at this model and we assume that we have a sequence where treatment 2 appears in periods j and j plus 1, then the j's observation is treatment 2 plus carryover effect of some other treatment, treatment 1, plus effect of the unit and so on. I neglect the period effect for the moment. And in the next observations, you have the same main effect. You have the carryover effect of treatment 2 now, because it appears twice. And the same assessor effect and the same interaction here. So if you take the difference between the two, it's there must be some expectation missing. It's the difference between the two carryover effects. And this disappears, but you have the difference between the two measurements, of course, between the two errors, which I've forgotten. But if gamma goes to 1, the variance of this thing goes to 0, and in the end, as gamma goes to 1, you estimate the difference between the two carryover effects is variance 0. And therefore, in the limit as gamma goes to 1, the small proportion of sequences with identical pairs allows to estimate the carryover effects with variance almost 0. And then the other sequences can be used to estimate the direct effects with the same precision as if there were no carryover effects. And that's exactly the variance from the upper bound. And we therefore can show our result 2 for all p if gamma goes to infinity. Is it infinity? I think I mean 1. I do mean 1, yeah. The optimal design will actually attain the upper bound. And so there was no way to improve largely. Yep. So that brings me to the end of my talk. Just a few remarks. That's the thesis that we had that Andrea wrote in 2009. Then we started working on it while we were here. And last week we got it accepted. We got the letter of acceptance for this article. So it's a nice roundup, and I'm extremely euphoric for being here anyway, and I'm extremely thankful to Rosemary to make it possible for me to come again. But this added even a slight epsilon to my happiness. Thank you very much.
I've got time for questions.
Joachim, did you think about practical validation of your optimal designs with a reasonable number of periods, say maybe 3 or 4 after the session?
I haven't got any beer with me. Actually, the main message of this paper is that we wouldn't use repeated assessments of the same product, even so this comes out here as being optimum. What's quite nice is that we can calculate the efficiency of the best binary design and see that if somebody is willing to repeat some treatments, we can at least give a bound and say, even if the model is completely correct and if you know the variance, the gamma, then you can win at most that much. So the practical message, of course, is with all the experiment that I do with students or with, I usually do it with children and not with beer. So I do it with children and they don't drink beer. So we don't give them the same product twice. We use the best design, the best binary design. But I don't have, as I said, I have no beer with me. You can have some water, but I don't think that will be very sensible to do an experiment with water here.
No? Thank you.
Okay.